Welcome to this week's Physics Colloquium. Our speaker today is Brad Marston, sitting over here, as you may recognize. Brad's known by many people in the physics department, participates in the Boulder Summer School from time to time, in particular 2 years ago. Brad received his PhD, looking at his history, from Princeton, and then postdoc to Cornell before he joined Brown University as a professor back around 1990. After he joined Brown as a condensed matter physicist, his interests expanded to include climate science. And Brad is a very well-known climate scientist, and his talk today is going to be about this intersection between condensed matter physics and climate science. Brad is also the vice president of the American Physical Society this year and will be taking over as president soon. 2025 or 2026? Okay, still has a little while before Brad is a professional politician. So please join me in welcoming our speaker today, Brad Marston.
Thanks, Mike. I'm recovering from a cold, so hopefully my voice will last. I'm married to a virologist, so she made me test twice before I came here. And so it's not COVID, or at least she would say it's below the level of detection. So I want to tell you about this work that my collaborators and I have done on waves of topological origin in the fluid Earth system and beyond. The surprising connection we found between the quantum Hall effect and waves in the atmosphere and the oceans of Earth. And I think this talk illustrates some of the problems with the siloing of physics into different fields, because a lot of the results I'll be telling you about could have been discovered many decades ago if there had been greater communication between the different subfields of physics. So that's going to be a part of my story. So this latest paper here that just came out in the Journal of the Atmospheric Sciences is something I'm looking forward to telling you about, where we looked at actual observations of Earth's stratosphere to discern non-trivial topology. So I want to begin from this quote by Richard Feynman that you can find in the Lectures of Physics. He said, "The next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence one sees between rotating cylinders. This is the rotating Couette flow. Today we cannot see whether Schrodinger's equation contains frogs, musical composers, or morality, or whether it does not." So I'm not going to attempt to address that final sentence, but the thrust of this talk will be in some small step towards understanding the qualitative content of partial differential equations from using this tool of topology that gives us a kind of shortcut to understanding, and also a new way of looking at things. And so the theme is that topology can turn some complicated problems into simple ones. So just to recall, what is topology? It's basically a statement about the qualitative shape of things under continuous deformations, where we're not allowed to tear them. And so these things may be physical objects, but more often they're mathematical objects, manifolds, things that have some sense of continuity. And so a typical example is this idea that the coffee mug could be continuously deformed if it was made out of Play-Doh into a donut, because both of those objects have a single hole in them. And if you were to try to get rid of that hole, you would have to either cut the donut, tear it apart, or smush it together, which isn't allowed under those rules. Another famous example is the Mobius strip, where here this paper is a non-orientable surface. What seems to be the outside of the surface here eventually becomes the inside of the surface. And so this is distinct from another piece of paper that's wrapped around without a twist in it. And again, you would have to cut the paper in order to transition from one to the other. An example that's a little bit closer to what we'll be talking about is the so-called hedgehog theorem. So if you consider a spherical hedgehog, which this is a pretty good approximation of, covered with quills, and you wanted to comb those quills flat, then there would always be some point where there's a defect, a bald spot, or a tuft where the quills come off of the surface. And so there's a topological obstruction to doing that, and that's called the hedgehog theorem. And we don't have these in North America, but I was on sabbatical in France, and when the seeds of this work began with my French collaborators, and we had a hedgehog in our backyard that I uncovered when I was raking leaves. It was going into hibernation, and I had to figure out what to do. But I like to think that this was like sending a signal to me to pay attention to topology, which at that moment I was too dense to really perceive. So the outline of this talk is I'm going to tell you a little bit about some climate science, the El Niño Oscillation, which is the largest climate oscillation on the time scale of a few years, and Kelvin waves that play an important role in it. And we're going to look at some observations and simulations. Then I'm going to change gears a little bit and talk about broken discrete symmetries that we're familiar with in physics, and the quantum Hall effect, a seemingly totally different topic. That's going to lead me to the shallow water equations, which we're going to look at in terms of their topology, and the mathematics of this is no more difficult than diagonalizing a 3x3 matrix. And that's going to lead us to the fact that these equations, the amplitudes of the waves, show non-trivial topology. And that makes some predictions about the kinds of waves we could see in the fluid Earth and fluid oceans in the atmosphere. And in particular, we'll look at the stratosphere, observation of the stratosphere, and try to discern this topological Whiting number. So a lot of these ideas carry over to magnetized plasma, and we've been doing an experiment with plasmas to try to look for these waves that I want to tell you about. So this is a view of the sea surface height of the Pacific Ocean as measured by satellite, reflecting radar, basically, microwaves off of the surface of the ocean. Red is higher than average, blue is lower than average. The amplitude is about plus or minus 20 centimeters. So this data has been filtered to remove tidal waves and higher frequency waves. We're going to focus on lower frequency waves. We're going to see a movie of the El Niño in the year 2009 to 2010. El Niños typically start around in the winter, and the reason that there's a red color for the higher sea surface height is that it's reminding us that this is correlated with warmer water, and warmer water expands, and so that's why the height is higher. So if I set this into motion, you'll see this pulse going right along the equator. That's the equatorial Kelvin wave. And when there's a pool of warm water off of South America, then we say that the Earth is in the El Niño phase, and it has widespread effects on the weather of the planet. Right now, we've been in the El Niño for a while, but we're expected to transition into the opposite phase, the La Niña phase, where the warm pool is over on this side. But you see this sort of unidirectional motion over this time period of 3 months of this wave moving along, and that's going to be the focus of much of our attention. So during the El Niño, a number of things happen at least, or there's enhanced probabilities for them to happen. So there's this southward shift in the storm track, which tends to bring more precipitation to the American Southwest area, but it's not a sure thing. So, for example, last winter, we were in a La Nina phase, and there was a very heavy winter. So it doesn't always hold up because there's lots of other oscillations going on in the Earth system. But you can see that it has effects all around the globe, even though it's primarily associated with the equatorial region of the ocean. So back when I was a graduate student, I started to get interested in climate science, and I was playing around with the observations of the Earth's temperature. And here, this is showing the Earth's temperature in the equatorial region from around, let's see, 1958 up to around when my PhD was ending. And you can see these oscillations. This is primarily due to the El Nino. So during the El Nino phase, the Earth tends to be warmer. But there's also a strong correlation with carbon dioxide being added into the atmosphere. And this correlation has persisted up to the present day. And it's not the greenhouse effect, but rather it's the idea that when the Earth is warmer than average, but due to the El Nino, then more carbon is emitted from natural sources such as forests that might be, there may be a greater probability for a forest fire in the tropics into the atmosphere. And so this represents a kind of positive feedback, because under the effects of global warming, we might expect that these carbon reservoirs will add their carbon to the atmosphere, further enhancing the global warming. And back here in 1991, we didn't really understand this very much. A lot more is understood about this carbon cycle and how it's affected by the El Nino. So that's just to say that this is an important oscillation. And so now I want to get at some of the physics behind this Kelvin wave that's associated with the El Nino. And I want to look at a two-layer fluid model. So in cross-section, I have a less dense fluid lying over a more dense fluid. So this is what we say is stably stratified, because the more dense fluid wants to be below the lighter fluid. This could be water and oil, for instance. Or it could be water at two different temperatures, a higher temperature up above and a lower temperature down below, as in the case of the ocean. And so this would be what we would call an internal wave between these two layers of the fluid. And if we drop a rock onto a spherical ocean, so a planet, imaginary planet that contains only ocean, no continents, then waves propagate out as they would for a rock dropped in a pond. And they go to the antipode, and then they come back, though, because we're on this sphere. And that's because gravity is providing a restoring force that allows for this oscillatory motion of the waves. And you can see that here in the cylindrical projection of the Earth. So going out to the antipode and back. So now, this is a non-rotating planet. I want to do exactly the same numerical experiment, but put the planet into rotation. And that will mean that there's an additional restoring force, the Coriolis force, that acts in the horizontal direction. And what it's going to do is if there's a parcel of fluid that's trying to move towards the North Pole, it's going to be deflected back to the equator and move eastward. So same initial conditions, everything's the same, except now let's look at a rotating sphere. And now we see that this wave is confined to the equatorial region. We can say that the equator is like a waveguide that traps this wave. And this is the Kelvin wave. You can see it's non-dispersive because this waveform, this wave packet is not distorted as it's moving along. There's a second equatorial wave that moves in this eastward direction that's anti-symmetric with respect to the equator, and it's called the Yanai wave. And you can see that its phase and group velocities do not equal. So we have this kind of phasing appearance and spreading of the wave packet, the dispersive wave. And so we need to try to understand the origin of both of these waves. So these simulations were done using some code that you can run if you want for free. If you have a Mac computer, it's on the Mac App Store. I call it GCM, and it has a bunch of idealized models of planetary atmospheres or oceans, if you like. And it's fully nonlinear. I was just gently stimulating the fluid in those movies. So what you saw was in the linear regime. So let's look at this from the standpoint of symmetries. And I want to appeal to the CPT theorem, the idea that the combined operation of charge conjugation, reversing charges, parity or reflection, and time reversal leave a system invariant. But here, we don't have any charge. We're thinking about neutral fluid. So I'm mainly going to be focused on parity and time reversal. So if we have a spinning planet and we look at it in a mirror, the direction of its rotation appears to reverse. So the parity operation reverses the direction of rotation. But then if we reverse the direction of time, we run the movie backwards in time, that restores the sense of rotation. So the rotation vector will be pointing upwards. So this is invariant under the combined operation of parity and time reversal, but it separately breaks each of them. We can understand that algebraically by looking at the relationship between accelerations in a rotating non-inertial frame and those in an inertial frame, which are just given by Newton's law, F over m. And we have these two additional terms. If we have steady rotation, this is the Coriolis force, and the acceleration has two time derivatives, so under time reversal it remains invariant. The velocity has only one time derivative, so it changes sign. So omega has to change sign under time reversal. So that's just reflecting the same physics as the figure. And most of the motion of the fluids are in the horizontal direction. So in thinking about this cross product, it's the local vertical component of the angular rotation rate that matters. So here we are in Boulder. We look straight up, and we take the dot product between our unit vector pointing straight up and the rotation vector coming out of the North Pole. And that gives us 2 times omega times the cosine of the latitude. So it vanishes at 0. Well, so this is the co-latitude. So it is going to be maximal at the 2 poles and vanishes at the equator. It changes sign at the equator. It's positive in the northern hemisphere and negative in the southern hemisphere. And it's given the symbol F because it's the same thing that appears in the Foucault pendulum that determines how quickly the Foucault pendulum precesses. And I forgot to check, but I think you probably still have a Foucault pendulum out of the tower, right? So what this means is that the 2 hemispheres of the Earth break time reversal symmetry in an opposite sense. And the equator is an interface between these two faces. And so for those who have been attending condensed matter seminars, this will immediately suggest itself as ripe for having waves of topological origin. But we still have to do some work to show that there's really topological physics involved. So let me divert briefly to the work of David Thales that was recognized in the 2016 Nobel Prize, where he provided the modern explanation for the quantization of the conductance in the quantum Hall effect. So there's David Thales. And so the quantum Hall effect, we have a thin semiconductor layer that's in a magnetic field. And it's observed that the transverse response the current in the transverse direction has these plateaus. And mechanistically, we can understand a little bit about that by noticing that the cyclotron orbits of the electrons in this magnetic field are nice circles here in the interior, but on the edges, they aren't going to make a full circle, but instead they're going to skip along the edge. And so there's going to be a unidirectional motion. And that means that if there's some dirt or impurities, as there always is in a condensed matter system, that won't have much of an effect on this current. It won't be able to backscatter the current because the current's just going in one direction. So that's what we call topological protection, but it was the explanation rooted in the mathematics of topology, which isn't really evident in this picture, but is what Val has touched on, that provides the rigorous explanation. I'm not going to repeat his argument here because it's going to be very similar for the case of our water waves. So let me turn to the simplest equations that support these kinds of equatorial waves. And those are the so-called shallow water equations. Shallow means that the depth of the fluid is going to be less than the wavelength of the waves. And so one can derive these equations systematically from the more fundamental Navier-Stokes equations by taking this limit. And so again, we have a similar setup as before. We have the height of this fluid, and then we have two horizontal directions. So the equations of motion for this fluid are an expression of conservation laws. So the first equation tells us about the time rate of change of the height, and this is the conservation of mass. And it simply says that if this bulge of fluid, say, is pushed out, squashed down, there will be a divergence in the fluid expressed by del dot h times u. U are the two components of the velocity in the horizontal direction. So that's a divergence. This is a positive number. That means that the time derivative of the height must be negative, and so the height is going down. So that's just saying that the fluid mass is conserved. And the second equation is just F equals ma. The acceleration is has these two restoring forces. The force of gravity, the acceleration of gravity. So the gradient of h is telling us that the gravity wants to push this bulge down, and then there's the horizontal component of the Coriolis force that's acting at right angles. The only subtlety is that since we're talking about a fluid, this derivative actually includes this nonlinearity, which is what's called the advective nonlinearity, and it simply reflects the fact that if we want to follow the acceleration of a fluid parcel, we can imagine putting some dye in our fluid, and we need to follow that parcel of fluid as it moves. And so we need this additional term in order to correctly account for the acceleration. So we're going to make some approximations. We're going to assume that the amplitude of this wave is small compared to the average height, the mean depth of the fluid, which I'll call capital H. And I'm going to replace this little h by a big H to make this first equation linear. So there's going to be little h here and u here, but there's not a product between little h and u, just big H. And I'm also going to drop this term because I'll assume that the waves are moving slowly so that this quadratic nonlinearity is small. And then I'll be thinking about this three-dimensional, these 3 degrees of freedom, the x component of velocity, which we sometimes call u, the y component of velocity we call v. So for geophysicists, the y direction is the north-south direction, and the x direction is the east-west direction, and then the height. And now I want to just look at the normal mode oscillations of this fluid. So let me put it on a doubly periodic plane. And so I can use plane waves. There's translational symmetry. The derivatives are replaced by wave numbers, kx and ky. And we have to diagonalize this 3x3 matrix to find the frequencies of the oscillation. So that's just a normal mode problem that's easily diagonalized. The fact that there's an I, a square root of -1 there, immediately tips us off that this linear operator, which kind of looks like a Hamiltonian, breaks time reversal symmetry. So if we diagonalize it, the eigenvalues, so we have one eigenvalue has exactly 0 frequency. And this is just the idea that around in the northern hemisphere, if we have a high pressure zone, the air or water circulates in a clockwise way. We have a balance between the pressure gradient and the Coriolis force. And conversely, a low pressure region has the fluid oscillating in the opposite direction, so that there's no sense of oscillation there. So there's exactly 0 frequency. And then we have these two other frequencies, positive and negative roots. There's always a positive and negative root combination because the fluid amplitudes, the wave amplitudes in real space and time are real valued functions, unlike in quantum mechanics, where the wave function is this complex valued thing. So they come in these conjugate pairs. But the dispersion relation looks like this. These kind of these hyperbolas, and then here's this a 0 mode, 0 frequency solution, and here's the two wave numbers and frequency. And I've colored the two bands, the two non-zero frequency bands, in a particular way that I'll explain in a moment. So if we have eigenenergies, or really eigenfrequencies, we have eigenfunctions, or wave amplitudes, and this is the form of them, and you can see already that there is something interesting going on. That just from diagonalizing this, there is a sense in which the phase of this amplitude oscillates very rapidly near the origin in wave vector space. In fact, it wraps around by 2 pi right around the origin. And I'm going to give you a graphical illustration of that here. So I'm going to imagine varying f from the south pole to the north pole through the equator where it's 0. And here's our dispersion. And this is a graphical display of the phase of the amplitudes. It's really the relative phase between the velocity, the v component, the y component of the velocity, and the height. And we have an anti-vortex in the phase. So these arrows represent the argument of the complex number, complex amplitude. And so if we go around the origin in a clockwise direction through 2 pi, then the arrows are actually rotating in a counterclockwise way through 2 pi. So we say that it has a winding number of -1. And so I've colored this top, that's for this top band, the positive frequency band. I've colored it blue to remind us that it has a winding number of -1. And this is the definition of the thing. This product between the two components is basically the relative phase, which again, between the y component of velocity and the height. That is what we say is gauge invariant, because the normal modes are defined only up to an overall phase. So we want to get rid of the overall phase and just look at the relative phase difference. And we can do that by multiplying v times h star. Now at the North Pole, the bands are reversed because the positive frequency waves have a vortex. They have a winding number of +1 as we go around in this wave vector space. The complex amplitude picks up a phase of +2 pi. And so we can then guess that something interesting is going to happen at the equator, because this band, this positive band, needs to somehow map on to the positive band up here. That is the negative frequency but positive winding number band has to somehow become a positive frequency band. And right at the equator, there's no Coriolis force, and the dispersion looks like a Weyl fermion dispersion. For those who've been thinking about graphene, the two bands touch, so they no longer have definite topology, because we've now torn our system. We've done something that's not allowed by our topology. So I've colored them purple, but so this is a topological transition as we increase f from negative values to positive values. And that tells us by this principle known as bulk interface correspondence, which we see in many, many systems, quantum systems and also optical systems and mechanical systems, that there are going to be, excuse me, some waves traversing the gap between the lower band and the upper band. Here, this is a dispersion where I've now allowed the Coriolis parameter to change linearly across the equator. So it's not fixed to be 0, but I now allow a spatial dependence in the north-south direction. So this involves solving a partial differential equation. This is not trivial, but it's not that hard to do. And we get this dispersion where we have the gravity waves, which are these two bands. We also have the flat band, the completely flat band, now becomes dispersive because of the Coriolis parameter depending on latitude. These are known as Rossby waves, which are very important in the weather systems. And then we have these two waves that we saw before, the Kelvin and Yanai wave. We have two waves because the winding number changes by 2, from -1 to +1, as we go across the equator. So this, in a nutshell, is the topological reasoning that brings us to the understanding of the origin of these waves. And we can make contact even closer to what was done with the quantum Hall effect by calculating the Chern number. The Chern number is the thing that David Thales was considering when he was calculating the conductivity in the quantum Hall effect. The Chern number changes by 2 going across the equator. And we now know from many examples that this implies the existence of these two waves. Okay, so these waves were found by direct calculation by geophysicists in the 60s, as I said, by allowing Coriolis parameter to change continuously across the equator. And this is the kind of dispersion that they found. This is in a textbook of geophysical fluid dynamics. And you see the 4 different types of waves: the gravity waves, planetary waves or Rossby waves, Yanai waves, Kelvin waves. There are different names for some of these waves, but there are these 4 sets. And when we submitted our paper to Science, we got this remark from one of the referees: the question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I've asked the question myself and been unsatisfied with my own answer, as well as the answers of other geophysical fluid dynamicists. So there's this sense that there was something mysterious about these two waves. They could see that they directly came from solving the wave equation across the equator, but why there were just these two waves instead of these bunches like we normally encounter? There was something missing in the understanding. And now this topological argument provides us with that kind of understanding. So condensed matter physicists have been focusing a lot on topological insulators in the past several decades. And one of the ways that they look for these kinds of boundary waves is by measuring their dispersion using angle-resolved photoemission experiments. But geophysicists have done exactly the same thing. And so the idea is that as this pool of warm water moves across the equator, we can track it by looking at clouds, because clouds are enhanced by this warm pool of water. And so by looking at from space at the cloud brightness and Fourier transforming that into wave vector space and frequency space, a dispersion relation for the waves can be recovered. And that was actually done here in Boulder by George Colloquium, who is famous for his work on tropical waves. And so here's the kind of dispersion that's seen in our topological insulators. Here's the theoretical prediction. And this is from a paper by Colloquium and Wheeler, where they look at the symmetric part of the cloud brightness spectrum. This is the zonal wave number. That means the wave number in the east-west direction versus the frequency, and we can see this Kelvin wave here. And then if we look at the antisymmetric part of the cloud brightness across the equator, then the Yanai wave becomes apparent. So the dispersion was seen in these measurements from space of the cloud brightness in a rather close analogy to what is done with angle resolved photoemission spectroscopy. Well, we were asked the question, well, we're not dealing with some tiny piece of condensed matter. We're living inside a topological insulator. So maybe we can use that fact to make more detailed probes of this topological insulator. And so climate scientists have accumulated large data sets that are basically a description of the weather of the past weather of the Earth over many years. And so we decided to use those to calculate this gauge invariant winding number that I calculated theoretically before. And so just to remind you that the theoretical prediction is for this vortex or anti-vortex if we're at sufficiently high frequencies. If we look at the lower frequency Rossby waves, we find out that those are topologically trivial because the wave amplitude vanishes right at wave number kx equals 0. And so by the rules of topology, we can't go across that tear. We don't want to go across the tear. We have to stay in a region where the magnitude of the amplitude of the waves is non-zero. So these are topologically trivial. These are topologically non-trivial. So after some trial and error, we settled on looking at the stratosphere of the Earth because the stratosphere is stratified. That means that it will support these kinds of gravity waves, unlike the troposphere, which is much more turbulent and less stratified. There's a reason why planes flying up at altitude typically have rather smooth conditions. Excuse me. Now, there's some interesting things happening up in the stratosphere near the equator, and one of those is another oscillation. It's called the quasi-biennial oscillation, and it's really beautiful because it's so periodic. So very few oscillations of the climate system are so regular, but this one is called quasi-biennial because it occurs every approximately 28 months. And what you're seeing is time and year for measurements from 1965 to 1990, and the colors represent the sign of the velocity of the winds in the east-west direction. And so what we're seeing here is this height is a reversal in the direction of the winds at the equator when we go up into the stratosphere above 20 kilometers. And there's also some interesting structure of the time dependence of these reversals. And it's believed that Kelvin waves may be part of the story of this quasi-biennial oscillation. I don't have time to go into the mechanism of this except to say that it's supported by gravity waves generated from the troposphere that are going up into the stratosphere, or at least that's the general idea. So we decided to go up to 20 kilometers and look at this data. It's called reanalysis data because the irregular spatial network of satellite measurements, balloons, and so on is supplemented by weather models. And so again, we're going to look at lower frequency Rossby waves and higher frequency Poincaré waves. And if we look at this winding invariant, we see that there is this barrier, this place where the amplitude goes to 0, right at wave number 0, as we expected for the Rossby waves. The frequency here is in cycles per day, so this is just a fraction of a Earth day period. But if we go up to the higher frequency waves, 1.5 cycles per day, then we can see that we have a vortex in our wave. amplitude. So in qualitative agreement with our very simple shallow water model, this is, of course, is a fully nonlinear, three-dimensional system, and yet we can recover the non-zero topology, the non-trivial topology of this system. We looked for a seasonal dependence. This is now looking at the correlation between the east-west component of velocity and the height field, so that the direction of the phase rotates by 90 degrees, but there's still a vortex. We can see the vortex through the four meteorological seasons: December, January, February, March, April, May, and so on. But if we go down into the troposphere, actually not too high above the elevation of Boulder, then this all breaks down. Because this troposphere is very turbulent, there's a lot of other waves going on, and we no longer have this topological signature, and we don't expect to see one because the stratification is so much weaker in the troposphere. So a few years ago, we were searching for a condensed matter experimentalist, and I was on the search committee, so the candidates were coming through my office, and I handed them this book, and they wondered why I was giving them a book on geophysical fluid dynamics, but there was a bookmark there. I asked them to open it up, and they came to this figure, and as soon as they saw that, all of the candidates immediately understood why I was showing this to them, because it looked exactly like the kinds of things they've been seeing time and again in condensed matter seminars, with a mode that is between this gap in this insulating phase. And so I barely had to say anything in order for them to understand the analogy to the geophysical system. So if I had been paying attention more myself, I could have realized this connection a lot earlier than I did. I wasn't really focused on the equatorial regions of the Earth, for my interests were sort of at the mid-latitudes. But there's this siloing, of physics, so that we don't have geophysicists talking to condensed matter physicists. And if condensed matter physicists had been aware of these kinds of waves, they would have known about a paper that Kelvin wrote over 100 years ago, where he wrote down the first wave of topological origin. So Kelvin's waves, he wasn't thinking about the equatorial Kelvin waves. He was thinking about coastal Kelvin waves, like in the English Channel. But again, he was looking at the shallow water equations subject to both gravity and rotation. And so we can do a laboratory experiment to illustrate this. So this is a wave tank with oil on top of water. And there's a wave source here, which is emitting waves in all directions. This tank isn't rotating. But if we put a tank into rotation, and so the camera is rotating with this tank, then we see these edge modes propagating in a unidirectional way. That's the coastal Kelvin wave. So here's Kelvin's paper from 1879. It's very easy to read. It's only like 3 or 4 pages long, on gravitational oscillations of rotating water. And here's the wave function he derives for an exponentially localized wave, localized to the coast, with a linear dispersion. And so, although he didn't have the topological explanation that we have for this wave, he wrote it down. And I could easily imagine that people studying the quantum Hall effect, if they had known about this work or paid attention to it, could have perceived that the edge mode of the quantum Hall effect was a single channel carrying E squared over H conductivity given by this kind of relationship. So I think this is probably the first time that such a mode was written down. And Kelvin actually was very interested in topology, so he thought about vortex rings and so on in real space. So it doesn't take a great leap of imagination to think that he would be able to easily follow the arguments that I've given here today. And you can read a little bit about the history of this in this Quantum Magazine article that came out last summer. It talks a little bit about our work, but also about Kelvin's work. It's a little bit overwrought in its title, but that was probably set by the editor, not the writer. So we're wondering if this kind of tool can now be put to use understanding other types of waves in the climate system that are much more poorly understood. And one of those is called the Madden-Julian oscillation. It's a eastward moving patch of rainy weather, and it goes right along the equator. So clouds are very important to this oscillation. That seems pretty clear. And some people have suggested that a Kelvin wave is involved in this. So we could now imagine looking at either simple models of this phenomena or observations. We could try to discern whether there's some topological signatures there or not. Maybe we can rule out some of the many models of this Madden-Julian oscillation, which also has global impact. My French collaborators have been applying these topological ideas to the interior of stars, where many stars have a transition between an inner radiative zone, which is stably stratified, and an outer convective zone, which might have very neutral stratification. And so they predict a topological wave due to a topological transition that might be observable in helioseismology or astroseismology. At this transition point between the radiative interior of the star, well, the sun anyway, which seems to rotate uniformly, and the outer convective region, which has some differential rotation, is a region called the tachocline. And these authors have suggested that there might be some waves of topological origin there involving both rotation and magnetic fields. So we've brought these ideas to fluid plasmas. Most of these, the earlier examples of topology were applied to lattice systems, crystalline solids, or optical lattices. But a major point that we made was that actually these ideas also apply to continuous fluid systems, although some mathematical subtleties need to be considered. So a magnetized plasma is a natural place to look because the magnetic field breaks the time reversal symmetry. So we've been doing an experiment at the Large Plasma Device at UCLA, which is a national facility. It is basically a large solenoid. And again, because it's this huge macroscopic thing, we can insert probes into the plasma and generate, have a transmitter for microwaves, and then try to pick them up and try to detect some sense of helical motion. So this is just the machine in operation. The flash is the plasma, and it's confined to sort of a cylindrical geometry going down the length of the solenoid. And so there's an interface between the plasma and the vacuum outside of the plasma. So the plasma is confined to the inner part of the cylinder, and then the plasma density drops off. So that's where we expect to find this topological wave. And so this is just our theoretical prediction of this this mode here. We called it a gaseous plasmon polariton. And a simulation that one of my students did showed that even if we have some bump in the plasma density because of this unidirectional propagation, it doesn't backscatter as expected. If we're at the wrong frequency, if we're up here, then we see a very different character for those waves, the electromagnetic waves emanating from a point source. They don't have this unidirectional sense. So this is just showing, looking down the tube, we had many problems. Like this is one of our pickup antennas. We melted a lot of these antennas. I'm a theorist, so it was extremely challenging to work with this machine. It's very loud. There's huge turbo pumps. There was a section there was police tape around and a little sign that said, "This part is floating at 20,000 volts. Don't touch." So fortunately, there's PhD level staff there. We had adult supervision. So we had to build some high frequency electronics because we were working in a gigahertz frequency. Most of the waves that this machine is used for are at lower frequencies involving ion motion. And so we have some preliminary results, which we're still analyzing. But this is a plot of time versus basically radius away from the center of our plasma. And this is looking at the intensity of our microwaves at 3 gigahertz. And we seem to see some evidence for a localized wave, which we think might be our wave of topological origin. But more experiments need to be done to really understand this. Okay, I'm almost done. So I want to close with some other examples of perhaps some surprising connections between physics as taught in physics departments and climate science. So a lot of climate scientists, atmospheric scientists, physical oceanographers self-identify as physicists. Many of them have undergraduate degrees in physics. So, but what I'm speaking to is sort of the physics that's done in traditional physics departments connecting to climate science. So one excellent example is this satellite, the GRACE satellite, Gravity Recovery and Climate Experiment, where slight variations in the gravitational field have been used to monitor the melting of ice in Greenland, flow of water, and so on. It's a pretty nice, maybe it's obvious connection between physics and climate science. Here's a very surprising thing I learned about last summer at Aspen Center for Physics. The Sajdovye-Kitaev model, the mathematics of this model that's very popular right now among condensed matter physicists, is very closely related to something called the direct interaction approximation that a physicist named Bob Krejcinen introduced back in the 50s, trying to understand turbulence. Krejcinen, sometimes described as Einstein's last student, and he was extremely influential on the field of turbulence and came up with this approximation, which in retrospect we can see is actually very similar mathematically to the SYK model. So again, there was a missed opportunity for a dialogue between condensed matter physics and fluid dynamics here. I have a colleague, Baylor Fox Kemper, who I think some of you may have heard from last year. He gave a colloquium here, I think, who's using lessons borrowed from general relativity to try to improve models of the ocean, interior of the ocean, where one follows along surfaces of constant density, and those surfaces have curvature to them. So the wave motion tends to follow along these surfaces. And so if we can use differential geometry, we may be able to improve our numerical representation of turbulence and waves in the ocean. Particle physicists have used cloud chambers to study nucleation of clouds by cosmic rays. And some groups have been starting to investigate the use of quantum computers for climate modeling. I'm one of these groups, so we're just trying to see whether there's any potential for a quantum computer to perhaps advance beyond a classical computer. I'm kind of skeptical about this, but I wanted to see whether it was possible. So a few years ago, Nature magazine had an article, Physicists, Your Planet Needs You, and it was trying to argue that physicists in physics departments could contribute to climate science. And they picked a particular problem, that is trying to understand the role of clouds in the climate system, which is the largest source of uncertainty in climate projections, because typical climate models, global climate models, have a grid size of like 10 kilometers by 10 kilometers in the horizontal direction, so they miss a lot of the structure that is present in clouds, and clouds have a big impact on radiative transfer between the Earth and the Sun, and also infrared radiation going back out into space. And the American Physical Society has a topical group on the physics of climate. I helped establish it, but it's now under new leadership, and some really top-notch people are organizing this and bringing. It's the main purpose of this group is to bring together traditional physicists and climate scientists. So if you have any interest at all in climate science, you don't have to be an expert by any means. I encourage you to join this topical group. They have a terrific newsletter, and they organize sessions at the March meeting and the Division of Fluid Dynamics meetings. And so it's I think a bridge between the fields that's much needed. So thank you very much.
Thank you so much for that really interesting talk. Any questions for Brad? Yeah, Victor.
So, you explained to us how the waves now, boundaries so space this time time, so we'll point out that this is related to region that really enhance climate science and the legal climate
Yeah, that's a good question. So I think the development of this diagnostic tool is where we have potential for advancing things, because we can look at actual observations and try to find signatures of topology. And this is a completely different way of looking at data than has been used before. So whenever we have a new way of looking at data, we might expect to learn some new things. But it also raises some important theoretical questions, which is the quantum version of these topological waves. That's a purely linear theory, but our fluid dynamics is nonlinear, in some cases highly nonlinear. But we lack the tools for combining the ideas of topology and nonlinearity together. So I think there's a real area that could be explored that may lead to some further insights into these waves and into the role of topology. So if I repeat those experiments, those numerical experiments with generating that Kelvin wave, but with much larger amplitude waves, then what happens is the wave breaks. It becomes highly nonlinear. The energy still moves in the same direction, but it gets spread out in K-space. And so trying to understand that kind of physics, where it's confined in one dimension still, it's still a waveguide, I think there's a lot of interesting things to be learned there.
Here. Yes, here.
Is there a geophysical analog to topological protection of these modes?
Yeah. Yes. So one of the things you could do a numerical experiment where these waves hit an obstacle, and because they're moving in this one direction, they'll just go around the obstacle and keep on going. And whether that helps to explain the robustness of El Nino, I don't want to say at this point. But there's definitely the sense of some degree of topological protection. And that's also something that needs to be explored. With our plasmas, well, we want to put in some obstacles once we have a clear signature for these waves and see what happens too.
Other questions? So I could follow up on maybe what Victor was saying. So by understanding Kelvin waves, which have been studied over for many decades in the Earth, you're trying to improve understanding of a phenomenon that's well known.
Yeah.
Providing new insights from a different field of physics. And in other areas, for example, with your French collaborators, you're actually predicting phenomena
Yeah.
that exist inside stars from this approach. Are there predictions in climate physics that can be made that could actually produce new observations could be able to actually observe that haven't been observed in the past?
Right. I think we don't know yet, but I suspect so. So maybe with this Madden-Julian oscillation, for instance, I think that some of the simple models for that oscillation have a topological character, and some of them don't. And so we'll be able to use that to perhaps to distinguish between the two models, two types of models. Yeah, I think we're just at the start. So there are different types of waves of topological origin. I didn't emphasize things vertically propagating. That was sort of in the models of the stars. That's another area that could be explored more fully.
Very good. Any other questions before we break? Okay, well, let's thank our speaker again.
Thank you.